Hello and welcome to this section 7.3 video asynchronous lecture thing. So section 7.3 is all about inverse trig substitution. It's like U substitution where we specifically pick our U to work really nicely with the inverse trig functions. Okay, so let's recall why this might be helpful. It's because, remember, the derivative of the inverse sine of x is 1 over the square root of 1 minus x squared. We find that derivative with implicit differentiation, which maybe you remember. Also note that inverse sine is called arcsine, and like inverse tangent is called arctangent, and inverse secant is called arcsecant. But let's continue with these. The derivative of inverse tangent is 1 over 1 plus x squared, and the derivative of inverse secant is 1 over x times square root 1 minus x squared. So if we see something that looks like this, 1 over 1 plus x squared, or 1 over the square root of 1 minus x squared, something along those lines, when we take an antiderivative, we should expect to find things that look like inverse sine, inverse tangent, or inverse secant. So all in all, this whole concept of inverse trig substitution is going to help us find integrals of things that look like this. Where here, this is not a 9, that's the letter A. So some good rules of thumb. Let me scroll so we can see it all. If you see something that looks like the square root of a squared minus x, you can let x equal a sine theta. Now you might be thinking, that's weird. Like normally when we do u substitution, we let u be the really complicated looking thing. We find du. And we're doing something along those lines here. Technically, we're introducing a new variable called theta, and we're letting theta equal the inverse sine of x over a. It just so happens that if theta equals the inverse sine of x over a, then x is a times sine theta. So we're defining a new variable theta in terms of x. It's just easier to think of x being written in terms of theta. It becomes easier to work with. So all that to say, if we see something that looks like square root of a squared minus x squared, we should probably think about letting x equal a sine theta, and then dx is a cosine theta. If we see something that looks like the square root of x squared plus a squared, we should try and let x equal a tangent theta, right? That's because the inverse derivative of tangent theta gives us x squared plus 1. If x is a tangent theta, then dx equals a secant theta. And then lastly, if we see something like x squared minus a squared, so here previously we had a squared minus x squared, now we're dealing with x squared minus a squared. If we see x squared minus a squared, we should try and let x equal a times secant theta, and in that case, then dx equals a secant theta, tangent theta, and it occurs to me now, I should have written d thetas here, so pretend that I had those written the entire time. Okay, so with that in mind, let's take a look at some examples. Okay, these can be somewhat involved, and you're probably going to have to end up drawing triangles, but if you follow this general process here, you'll get where you want to go. So let's take a look at the integral of the square root of 1 minus x squared. Well, which of these three does it look like? Well, it looks like a squared minus x squared. So let's try letting x equal a times sine theta. So we're going to let x equal, in this case our a is 1 because 1 squared is 1. So x is sine theta, then dx equals cosine theta d theta. And this becomes the integral of the square root of 1 minus sine squared theta times cosine theta d theta. Hey, what do we know about 1 minus sine squared theta? Now, you can't see what I'm doing like a Dora the Explorer, wait for you to respond. Yeah, exactly. It's cosine squared theta. So this becomes the integral of the square root of cosine squared theta times cosine theta d theta. Square root of cosine squared gives me cosine. So this is the integral of cosine squared theta d theta. Right, the integral of cosine squared, the square root of cosine squared gives me cosine, multiplied by this cosine, I get the integral of cosine squared theta. Now you might be thinking, hey, the integral of cosine squared theta, I've seen that before. I saw it in the last section, section 7.2. So I know that this works out to be 1/2 theta plus 1/2 sine theta cosine theta plus c. And you're exactly right. So we found our integral. With one exception, right here, this is written in thetas. We'd really like it to be written in sine, in terms of x's. How do we do that? All we know is that x equals sine theta. Remember this drawing triangles that we talked about before? This is where it comes in. So if x equals sine theta, that means I can have a triangle here. Hopefully this snaps into being a right triangle. Perfect. I got a nice right triangle here. I've got my angle theta here. If the sine of theta equals x, that tells me that the sides of the triangle look something like this. Remember, sine is opposite over hypotenuse, so the opposite is x, the hypotenuse is 1. I suppose technically this hypotenuse could be like 7, and this could be 7x, but we can scale it down so that the hypotenuse is 1, because sine is scale invariant, which is a fancy way of saying the sine of theta doesn't change if I expand the triangle by 2 or shrink it by whatever number. Okay, so if I know that this side is length x and this side is length 1, can I find the length of this side? You bet I can, because of the Pythagorean theorem. I know that this side is the square root of 1 minus x squared. Right? The reason I know that is because this side length squared plus this side length squared better give me 1 squared. Better give me 1. So the only side length that works is square root 1 minus x squared. So then, with that in mind, cosine theta, remember cosine is adjacent over hypotenuse, cosine theta is the square root of 1 minus x squared, and theta is the inverse sine of x. It's also the arc sine of x, if you want to write that. That looks horrendous. There we go. So, if I want to trade my thetas back in for x's, I end up with 1/2 arc sine of x plus 1/2 x. Remember, sine theta was chosen to be x. And then cosine theta is square root 1 minus x squared. So this relatively simple looking function, just square root of 1 minus x squared, has a pretty complicated looking antiderivative. But the only way we could find that antiderivative is by using this inverse trig substitution. Let's see another example. Let's see it again. We want to find the integral of 1 over 4 minus x squared to the 3/2 power. Now, it might be helpful to think of this as being written like the square root of 4 minus x squared quantity cubed. And I suppose, although I haven't really prepped to do this yet, I suppose that's the same as just the square root of 4 minus x squared times 4 minus x squared, but I'm not going to get into that right now. Okay, so square root of 4 minus x squared quantity cubed. What does this look like in our kind of rule of thumbs? So remember, we have 4 minus x squared. And yeah, it looks something like this. Okay, so 4 squared minus x squared looks like a minus x squared. So we should try and let x equal square root of 4 times sine of theta. Or I guess more specifically, 2 sine theta. We should let x be 2 sine theta. Then dx is 2 cosine theta d theta. And let's see what we get. This becomes an integral of 1 minus the square root of 4 minus x squared. So that's 2 times sine theta squared. That's going to give me 4 sine squared theta cubed times 2 cosine theta d theta. So I'm just plugging my x equals 2 sine theta here, and I'm plugging 2 cosine theta d theta for dx. Now let's take a look at this 4 minus 4 sine squared theta. I have a 4 in front of both things, so I can factor out a 4. This becomes 4 minus 1, or 4 times 1 minus sine squared theta. And oh my goodness, that's exactly what we just worked with. That's cosine squared theta. So that's 4 times cosine squared theta. Okay, so with that in mind, my integral can become 1 over the square root of 4 cosine squared theta, quantity cubed, times 2 cosine theta d theta. But 4 cosine squared theta, when we take the square root of that, that's going to become the integral of 1 over 2 times cosine theta, that whole quantity cubed, all times 2 cosine theta d theta. Right, remember square roots distribute over multiplication. So square root of 4 times cosine squared, that's the same as square root of 4 times the square root of cosine squared. So this becomes an integral of 2 cosine theta over 8 cosine cubed theta d theta, which becomes, I guess, 1 over 4 times 1 over cosine squared theta d theta. Suppose I should have an integral there. Cosine squared, maybe this doesn't look like something you know how to work with, like how do we take the integral of 1 over cosine squared? Maybe it becomes a little bit clearer if I write this as secant squared theta d theta. Remember, because cosine, or secant is just 1 over cosine. And yeah. Integral of secant squared theta, that's tangent. That is tangent theta. So we get 1/4 tangent theta plus c. So we did all this work. We set x equals 2 sine theta, and we were able to rewrite everything and get 1/4 tangent theta plus c. Now, we have things written as thetas. We want to get them in terms of x's again, and so we're about to draw another triangle. So remember, x is 2 sine theta. So what does that mean? Here's this. Here's my angle theta. If I double my sine of theta, I'm going to get x. Another way to write that, perhaps that's a little bit easier, is x over 2 equals sine theta. So that means that this side length is x over 2. This side length is 1. Now, tangent of theta is opposite over adjacent. I know my opposite side from theta. I just need to find my adjacent side, but we can do that with the Pythagorean theorem yet again. It's very handy. So that's the square root of 1 minus x squared over 4, or x over 2 squared. So tangent theta is opposite over adjacent. So this works out to be 1/4 times x over 2 divided by the square root of 1 minus x squared over 4, which I suppose simplifies to be 1/8 times x over the square root of 1 minus x squared over 4 plus c. So to recap, we saw something that looks like a squared minus x squared. So we used our inverse trig substitution. We let x equals 2 sine theta. And after that, it's just pretty much just a standard U substitution. We had to use a trig identity to write 1 minus sine squared as cosine squared. And then everything worked out really nicely. And then in the end, we were left with an antiderivative in terms of thetas. We just had to trade that back in for x's. So those are examples of a squared minus x squared. Let's see something else. Here we have 1 over x squared plus 9. Okay, so going back to our rules of thumb, this one looks like this. It looks like x squared plus a squared. And so if it looks like x squared plus a squared, that means we should let x be a tangent theta. So let's let x equal 3 tangent theta. Remember, you can think of it as square root of 9. Simplifies to 3. Then my dx equals 3 secant squared theta. So let's plug stuff in and see what kind of simplification we get. This becomes the integral of 1 over the square root of 3 tangent theta quantity squared plus 9 times 3 secant squared theta d theta. So 3 tangent theta squared, that's going to be the same as, here I'm going to combine this. I'm going to put the 3 secant squared on top of this fraction here because it's a little bit less writing, a little bit less space. So we get 3 secant squared theta on top of the square root of 9 tangent squared theta plus 9 d theta. I've got 9s in both of these guys, so I can factor a 9 out. I get the integral of 3 secant squared theta divided by the square root of 9 times tangent squared theta plus 1 d theta. Now, you at home, you're probably on the edge of your seat. You're thinking, hey, tangent squared theta plus 1, that's secant squared theta. That's a trig identity that I learned. And you are exactly right. So this becomes the integral of 3 secant squared theta divided by got a little ahead of myself, the square root of 9 times secant squared theta d theta. But both of these guys, 9 and secant squared theta, those are squares, right? 9 is the square root of, or 9 is 3 squared, secant squared is obviously secant squared. So we get an antiderivative of 3 times secant squared theta over 3 times secant theta d theta. Those cancel out, This becomes an integral of secant theta d theta. And if we remember from last time, we learned how to take this integral. We learned that integral of secant theta, that is the natural log of the absolute value of secant theta plus tangent theta. And we're done, except for we need to trade our thetas back in for x's. So let's remember that x equals 3 tangent theta. So that tells me that tangent theta equals x over 3. So let's use that to draw a triangle. Perfect. Nice right triangle here. If this is theta, we know that the tangent of theta is x over 3. So then this side length here, the length of the hypotenuse, has to be the square root of 9 plus x squared. Okay, so then what does that tell me that secant of theta is? Well, remember that secant of theta is 1 over cosine theta, or 1 over cosine theta. And so this is 1 over cosine of theta is adjacent over hypotenuse. So this is 1 over 3 over root 9 plus x squared, which simplifies to root 9 plus x squared over 3. So write this a little bit neater. We find that secant of theta, which you can think of it as 1 over cosine theta, you can also think of it as hypotenuse over adjacent, works out to be root 9 plus x squared all over 3. So finally, our final answer is the natural log of the absolute value of the square root of 9 plus x squared over 3 plus the tangent of theta, which we already know is just x over 3. Plus c, got to have that constant of integration. All right, another example to hopefully kind of drive this idea home. The integral of 1 over x squared times the square root of x squared minus 9 dx. So we've already seen examples that look like a squared minus x squared. We've seen examples that look like a squared plus x squared. Now we have an example that looks like a squared minus, or x squared minus a squared. And if we remember from our general rules of thumb, if we have something that looks like x squared minus a squared, here my a is 3, because 9 is 3 squared, we should try and let x equal 3 secant theta. If my x is 3 secant theta, then dx, well, that's the same as 3 secant theta tangent theta d theta. So I'm going to plug in a 3 secant theta every time I see an x, and I'm going to plug in a 3 secant theta tangent theta d theta every time I see a dx. Doing so, I get an integral of 1 over 9 secant squared theta, right? If I plug in a 3 secant squared theta in here for x, and then square it, I get 9 secant squared x, times the square root of 9 secant squared x minus 9. So maybe rewrite the fraction like that, times 3 secant theta tangent theta d theta. All right, I'm going to write this again. I'm going to move all this stuff on top of this fraction to save some space. I'm going to look here inside this square root. Okay, so 9 secant squared x minus 9, that should be a theta, not an x, sorry. But both of these guys have a 9 in them, so I can factor a 9 out. In doing so, I get an integral of 3 secant theta tangent theta over 9 secant squared theta times the square root of 9 times secant squared theta minus 1 d theta. And oh ho ho, what rears its ugly head again but the trig identity. Remember that secant squared theta minus 1, that's the same as tangent squared theta. So this whole guy becomes the integral of 3 secant theta tangent theta divided by 9 times secant squared theta times the square root of 9 tangent squared theta, all d theta. And let's take the square root of that 9 tangent squared theta, shall we? Shall we? We get 3 secant theta tangent theta over 9 secant squared theta times 3 tangent theta d theta. And look at all this beautiful cancellation. We have a 3 on top and bottom that cancel out. We have a tangent theta on top and bottom that cancel out. We have 1 secant theta on top and bottom that cancel out. And so we are left with the integral of 1 over 9 secant theta d theta. I don't know what the integral of 1 over 9 secant theta is, but I sure do know that secant theta is 1 over cosine. So this is the same as 1 over 9 times cosine theta d theta. And I sure do know how to take that integral. I know that that's I know that that's 1/9 sine theta plus c. Now I just have to figure out what sine of theta is. Let's recall that x equals 3 secant theta, or x over 3 equals secant theta is another way to remember that. X over 3 equals secant theta, so let me draw my triangle here. And if I've got my theta here, secant is hypotenuse over adjacent. So my hypotenuse is x, my adjacent side is 3. So I get x and 3 here. In order to find out the sine, I need to know this opposite side. And that's just Pythagorean theorem. We get x squared minus 9. So the sine of theta is square root x squared minus 9 over x. So we end up with 1 over 9 times the square root of x squared minus 9 over x plus c. Look at that. Plugging in 3 secant theta for x, this seemingly arbitrary thing, ends up to work out really nicely. And the reason it works out nicely is because this looks like the antiderivative of inverse secant. So we're letting x be 3 secant theta, and everything works out really nicely. Okay, so what if we have a more general looking thing? This is supposed to be a 3. What if we have something... This doesn't look like anything we've seen so far. X squared plus 2x plus 3. This doesn't look like x squared plus 1 or a squared minus x squared. What do we do here? Well, what we're going to do here is we're going to involve something called completing the square. So completing the square helps you find the roots of something like ax squared plus bx plus c. You use completing the square to find, you use the method of completing the square to find the quadratic formula, which is really nice. But completing the square says if I have something that looks like this, just some general quadratic thing, this is the same as a times x plus b over 2 quantity squared minus b over 2 quantity squared plus c. I suppose this should be b over 2a, and this should be a c over a. Okay, and turns out doing this completing the square thing is going to help turn this into something that looks like something that we know how to work with. It'll look like something that we use inverse trig for. So let's complete the square. Here my a is 1, because the leading coefficient is 1. My b is 2, and my c is 3. So this works out to be the integral of 1 over x plus 2 over 2 quantity squared minus 2 over 2 quantity squared plus 3. This is all raised to the 3 halves. Okay, it looks like the recording kind of cut out part way, but I think we got here. We explained completing the square, so I'll continue on from here. This becomes the integral of 1 over x plus 1 squared minus 1 plus 3 to the 3 halves dx. And minus 1 plus 3, that's the same as plus 2. Okay, so we have this x plus 1 hanging out. It's not very convenient, but we can get rid of it with a u substitution. If u equals x plus 1, then du equals dx. And so this becomes a much simpler looking integral, 1 over u squared plus 2 to the 3 halves du. And this 1 over u squared plus 2 to the 3 halves, this is the type of thing that we've already seen before, right? We know that if we get something that looks like the square root of a squared plus x squared, we should try letting x equal a tangent theta. So that's what we have here. We have our variable squared plus something squared, right? I guess the square root of 2 squared. It's not a whole number, but it's nice enough. And we have a square root here. We have this fractional exponent. So let's try letting u equal root 2 tangent theta. Okay, now it might be looking kind of weird because like, hey, we've already defined u as being x plus 1, and now we're defining it as root 2 tangent theta. But remember, technically what we're doing is we're defining the variable theta to be the inverse tangent of u over root 2. Just so happens that if we do that, then this works out really nicely. So we have this change of variables. If u equals this, then du equals root 2 times secant squared theta, d theta. And all in all, we get the integral of 1 over root 2 tangent theta squared plus 2, everything on the bottom to the 3 halves power, times root 2 secant squared theta d theta. D theta. And this square root 2 tangent theta squared, I'll square all that, and I'll move everything that's in here to the top, just to save on writing. This becomes the integral of root 2 secant squared theta over 2 tangent squared theta plus 2 to the 3 halves d theta. And now, hey, we've kind of seen this movie before, right? I have 2's here and here, so I can factor out a 2. This gives me the integral of root 2 secant squared theta over 2 times tangent squared theta plus 1, all to the 3/2 power d theta. But tangent squared theta plus 1, that's secant squared theta. So I end up with an integral of root 2 secant squared theta over 2 times secant squared theta to the 3/2 power d theta. And let's remind ourselves what these fractional exponents mean, right? So this means we take whatever's here, 2 secant squared theta, and we cube it and then take the square root, or alternatively, we can think of it as taking the square root, and then cubing it. And what's nice about this is that the square root of secant squared theta is really straightforward. So this is going to give me the integral of root 2 secant squared theta over square root of 2 cubed times secant cubed theta. So the square root of secant squared theta is just secant. I raised it to the 3rd power. Here I have square root of 2 to the 3rd power. Square root of 2 to the 3rd power is the same as 2 square root of 2. And so now I have my square roots of 2 on top and bottom cancel out. My secant squared on top and 2 of my secants on bottom cancel out. And so I'm left with the integral of 1 over 2 secant theta d theta, which that is the same as the integral of 1/2 cosine of theta d theta, and that is 1/2 sine theta plus c. So we found our antiderivative in terms of theta. Now we just want to write it in terms of u's and then in terms of x's. So remember, u equals root 2 tangent theta here. So this tells us that tangent theta equals u over root 2. So if I draw a triangle here to find out what sine is, here's my theta. What did we say it was? Tangent theta equals u over root 2. So opposite over adjacent is u over root 2. Now with that in mind, how do we find the sine? Well, we need to know the length of this hypotenuse. Sine is opposite over hypotenuse. The length of this hypotenuse is the square root of u squared plus 2, right? Because c squared is equal to a squared plus b squared, so u squared plus square root of 2 squared gives me 2. We take the square root. So sine of theta is u over root u squared plus 2. So my integral is 1/2 times u over the square root of u squared plus 2 plus c. But we want our final answer to be in terms of x's. So we recall that u, all the way back up at the front, is the same as x plus 1. So we end up with 1/2 times x plus 1 over the square root of x plus 1 squared plus 2 plus c. We get our antiderivative that way. So that is antiderivatives of, or I should say integrals or antiderivatives involving inverse trig substitution. So we pick our angle theta really carefully so that everything kind of works out in the end. And how do we know what we should let our angle theta be? Well, it all goes back to these rules of thumb. So if you see the square root of a squared minus x squared, you should consider letting x equaling a sine theta. And if you see the square root of x squared plus a squared, you should consider x equals a tangent theta. And if you see x squared minus a squared, you should consider a times secant theta. That is inverse trig substitution. Thank you so much.